Hello everyone, this is Shivani Agarwal. So today's my topic is number system. This is a topic of the computer organization and architecture basic topic. Just we have to define. I am the faculty from the Department of Information Technology, AKGEC Engineering College, Ghaziabad. So let's start. So what is number system basically? Number system is used for representing the information, and we have to communicate any information in the computer system in the binary form. So this is a not the particular language words, this is a binary number system, that is a 0-1 form. So number system has different bases. First is the decimal base, second is the binary base, third is the octal base, fourth is the hexadecimal base. Basically decimal base means we have the base means radix. Basically it is also known as radix. So what is base? Basically base means radix. Radix or base, both are same. Decimal base 10, any number base 10, this is decimal base, that means the range of this base is 0 to 9. Now binary base is binary, that is 2, range is 0 to 1, that is 0 to n minus 1. So it is this is n, so it is 0 to 1. Now octal base is 0 to 7 range, same as hexadecimal, that is base 16, so it is 0 to 15. 0 to 15. So basically number systems are two types. First is positional, second is non-positional number system. Positional means each and every element has some weight, and we have to represent the weight with the w, with respect to w, with each bit that is started by the 0. So the example of the weighted codes are, or a position number are, suppose the number is 5629. So we start from LSB. This is LSB. This is MSB. MSB and LSB means MSB is the least significant bit, MSB is the most significant bit. So the number is 5629 and the MSB bit is 5 and the LSB bit is 9. So in the positional number system, we have to define the 0 weight, initialize the 0 weight with respect to the base. So it is basically 9 multiplied by 10. 10 is the base. Position is 0, start with 0 from the LSB part. Now move on to the next part, the next bit, that is 2. 2 multiplied by 10 to the power 1, it is increasing from 1 by 1. Now it is 0 to 1, then 1 to 2, 2 to 3. So it is just increasing from the LSB to MSB with the numbers. So this is basically the formation of XW. X is the number, W is the weight. So it is basically XI, WI, right? Summation of Xi, Wi equals to Y. This is the output value. Okay. So X is the number, W is the weight, and the value of I is between 0 to n. Any value corresponding to the LSB bit and starting from 0. So this is the basic of the positional number system. Now similarly, it is a second example with the decimal number. So the number is 5629.6518. When the decimal number, then we start the counting from this side. This is left to right, right? So start not from the 0, because it is after the decimal or the fractional part, we have to start from minus 1, not the minus 0, because minus 0 counting is not considered in the binary number system. So it is basically minus 1. So it is 6 multiplied by minus 1, then minus 2, minus 3, minus 4 from left to right. So we have to define the number system in the decimal, in the fractional decimal number in the form of the weighted codes are minus 1 to minus n. This is corresponding from left to right positions. So each digit in the number system can be determined either it is in normal form or in the fractional form. In the normal form or the real number, we have to start from 0 from the LSB part, and in the fractional part we have to start with minus 1 from left to right motion. Now, in the non-position system, we have a number that doesn't indicate any significance in the position. That means there is no significance of the position part. There is no significance of the position and weight. So, 0 is absent in that case, and there are the Roman numbers also we have to use in the non-positional system. So, different type of number systems we have. How many types we have? The number system already defined, that is a decimal, that is binary, that is third is octal, and fourth is hexadecimal. So, that I already explained that the decimal number system have the range between 0 to 9 because it is 0 to n minus 1. What is the value of n in this case? In this case, the n value is 10 because it is the decimal number system. Then how we have to represent the decimal number system? So, let's take an example with the positional weight number system. So, it is 7739.4538. This is the example. So, when we have to define the decimal number system in the form of the weighted code as a real number or in the fractional number. So, when the real number it is started from this side, this is the LSB part, this is the MSB part, it started from 0 from there. Now, 1, 2, 3, these are the position of the weights with the value of x. With the respect value of x, suppose first value is 9, second is 3, third is 7 and fourth is again 7. So, we started from 9 multiplied by 10 ki power 0. This is the power base. This is basically x, base and the w. This is the basic formation of this particular system. So, this is calculated as 9 multiplied by 10 to the power 0 plus 3 multiplied by 10 to the power 1 plus 7 multiplied by 10 to the power 2, 7 multiplied by 10 to the power 3 plus the decimal or the fractional part lies as left to right, and starting from the weight values are minus 1. So, it is 4 multiplied by 10 to the power minus 1, 5 multiplied by 10 to the power minus 2, 3 multiplied by 10 to the power minus 3 and the 8 multiplied by 10 to the power minus 4. So, this is the resultant basically. Now, in the binary number system, we have the values or the range are 0 to 1, the base is 2, and when we have to represent any number, binary number in the decimal form, then how we have to calculate? We have to define as same 1 multiplied by base ki power w, that is 0, this is the position, this is 1 multiplied by 2 ki power 1, 1 multiplied by 2 ki power 2. So, these are the number representation system with either decimal, either binary, either octal or the hexadecimal. So, this is a octal, third number is the octal number representation. This is same as the decimal or the binary number. So, it is start from this 6 multiplied by 8 ki power 0. This is the basic representation or the mathematical formation that it is x b to the power w, where x is the number, b is the base, w is the weight, same as the corresponding with the decimal and the binary number system. So, this is the octal. Now, last is the hexadecimal. Hexadecimal, the range is 0 to 15 and the base of the hexadecimal is 16. But in the hexadecimal, we have the representation of the values like that. 0 to 9 is the normal numbers, but after the 9, we have to represent 10 like A. 10 representation is A. This is the recognition system of the hexadecimal. Now, 11th is B, 12th represented as C, 13th represented as D, 14th is E and 15th is F. This is the basic representation of the hexadecimal number system. So, always you remember that the number of 0 to 15 we have to represent in the hexadecimal. So, same as 0 to 9 as decimal, and after 9, that is 10 to 15, we have to define as A, B, C, D, E, F form. So, this is the basic of the hexadecimal number system. Now, move on to the next slide. These are the basic radix or n. These are the range, that is 0 to n minus 1. So, these are the basic that I already explained in the previous slide. Now, the convergence. These are very important part in the any number system logic, that is the decimal number system to the binary, binary to decimal, octal to binary, octal to hexadecimal, binary to octal, binary to hexadecimal, hexadecimal to binary, hexadecimal to octal. So, let us take an example from the one by one number system. So first is the any base to decimal. Any base means any base. Any base either is 1, 2, 3, 4, 5, any base to decimal. So let's take an example how we have to calculate. So there are the 3 steps that we have to calculate how the any base, we have to convert any base to the decimal form. So first step is determine the base value of the given number system. Determine the base value of the given number system that you want to convert. So this is the first step, and also determine the position of the digits from LSB to MSB, that I already explained that we have to start from the LSB to MSB with the positions of 0 to n. Okay. Now the second is multiply each digit with its corresponding multiplication of position values and base given number of the number system base. Third is add the resultant value into the step B. So these are the 3 steps. These are the basic common steps of the conversion of any base to decimal. So let's take an example. When the example is 1101.1, this is the binary number. So the base of this number is 2. And we know that if the number is the real number, then we start from LSB to MSB, and when the number of the fractional part, then we start from left to right with the position value of -1. So this is position is -1, this is -2, this is 0, 1, 2, 3. Corresponding, we have to calculate the decimal value. We have to multiply each number with the position weights with the corresponding to the base value. So the number conversion is like that: 1 multiplied by 2 to the power -1, sorry, 2 to the power 0, then 0 multiplied to the power 1, then 1 multiplied to the power 2, then multiplied to the power 3. And the fractional part we have to define as 1 multiplied to the power -1, and this one is multiplied to the power -2. So this is the basically binary to decimal number system. So the resultant we have to produce after the calculations like that. This is basically 2 to the power 3, that is 8, 2 to the power 2, that is 4. Now 2 to the power 1, that is 2 to the power 1 but multiplied by 0, so it is 0. Now 2 to the power 0, that is 1, 1 multiplied by 1, that is 1. Then the fractional part is 2 to the power -1, that is basically 1 by 2, so it is 1.5. Then 1 by 2 to the power 2, that is 1 by 4, so it is 0.25. After the calculation or the addition of these numbers, that is 13.75. This is the basic of binary to the decimal. So this is any base to decimal. Then let's take a second example. This is basically octal to decimal. Same procedure we have to follow from any base to decimal. So same multiplication, same the position value, same the position value in the real part, same position value from the in the fractional part, that is started from -1. So when the number is 475.25, then the number representation from the octal to decimal we have to represent like that. That is 5 multiplied by a to the power 0, that is the position. 7 multiplied by a to the power 1, this is the position of the second number weight. And now 4 multiplied by a to the power 2. And the fraction part is 2 multiplied by a to the -1, 5 multiplied by a to the -2. So the calculation is 317.32813. This is the basic, right? Now this is this is hexadecimal to decimal. So hexadecimal to decimal, we have to represent the same. That is start from 1 multiplied by 16 to the power 0. B means that is 11 basically. So this is 11 multiplied by 6 to the power 1. Now 7 multiplied by 6 to the power 2, and 0.2a matlab 0.2. 2 multiplied by 16 to the power -1, a multiplied by 16 to the power -2. After the calculation, the resultant is 1969.164. This is the hexadecimal to decimal. Now this is the example of any base to decimal. This is the base 4. This is the not defined, the defined weight. So let's take the base, that is the 4 base. Then we have to convert the number. So same procedure we have to follow. That is 0 multiplied by 4 to the power 0. 0 multiplied by 4 to the power 1. 1 multiplied by 4 to the power 2. 3 multiplied by 4 to the power 2. 1 multiplied by 4 to the power -1. And 2 multiplied by 4 to the power -2. So these are the basics when we have to convert any base to decimal. So this is the final answer. This is 64.375. So this is basic from any base to decimal. Now the second is decimal to any base. First we have to know that about any base to decimal. Now the second is decimal to any base. So how we have to follow a decimal to any base? So when we have to convert any number, any decimal number or any number to any base or decimal number to any base, then how we have to do the calculations? We have just divided method we have to use to convert from decimal to any base. So this is decimal number to base 2. So how we calculate this particular conversion? So we have to divide the number, the corresponding number that we have to want to convert in this particular base. So we have to divide this particular base value with the number. So this is a base 10 converted to base 2. So we have to divide 15 with the base value of 2. So divide 2, basically we have to do like that. Just divide 2, 2 7s 14. Now remainder is 1. Now again 2 3s are 6, remainder is 1. 2 1s are 2, remainder is 1. So the corresponding answer is from MSB to LSB, that is 1 1 1 1, base 2. So this is the answer. This is basic from decimal to binary base. Decimal to any base we have to convert. The same example. Okay, this is slightly changed when we have to convert any fractional number to any base. Then we have to use the multiply part from this particular value to the any base value. So the conversion base, converted base is 2 from the base 10. So how we have to do it? So when we have any fractional part, so we have to just multiply. For example, okay, let's take the same example, 0.18125 multiply by 2, then the resultant is 1.625. So we take the output as a real value, that is 1, and after the fraction value we have to take the another part, that is 0.625 multiply by 2. So the value is 1.25. So the resultant is 1 in this case. Again we take 0.25 multiply by 2 till this is 0.50. So resultant is 0 in this case. Then again 0.50 multiply by 2. So the resultant is 1.00. The resultant is 1 in this case, and we have to produce find the resultant from top to bottom in this case, not from the bottom to top. So the resultant is basically 0.1101 base 2. Okay, how we have to stop this particular step after the multiplication? So there are basically two methods. If we have to produce after the multiplication, we have to produce 0. So this is the stopping step that we have. If after the multiplication we have to produce 1.00, then we have to stop the calculation over there. Second method is that when we find out the repetition value, suppose 1.25 is in first time and second time again we have to calculate, and again 1.25 we have to find out the next step. So we have to stop the calculation till after the two values are repeated. So this is the basic method of the fractional value we have to represent from the decimal to any base. Now take the next example. So next example is decimal to base 8, because we change the base value from decimal to any base. So we take the value of 8. The number is 214.640625. So we have to divide 214 by 8. So after the division, it is basically 8 to the 16. Basically, how the value is received. This is 554. Now remainder is remains 6. After that, now this is 26. So it is 8 here 24. So this is basically 3 is present here, and the remainder is 2 over there, because 26 minus 24. The basically remainder is 2 over there. Now it is 3. So basically the answer is because we start from the bottom to top after the division. So it is 3 to 6 is the answer of the real part, but the fractional part we have to just multiply. So multiply by 8. So 0.640625 multiply by 8. So it is basically 5125. So the resultant over there is 5, and 0.125 again we have to multiply with the 8. So it is basically 1.0. So the resultant is 326.51 base 8. Now this is the next example. This is 54 base 10 converted to any base. So I take the example of the base 4. So we have to just divide 54 by 4. So basically 4 1 is 4. Basically after the division, how the value produced is 1. So 4 2 is 8, 4 2 is 12. So basically it is 3. Now after the subtraction of the 14 minus 12, that is 2. So this is the remaining answer is 2. Again divide by 4 from 13. So 4 is 12. The remainder is 1 in this case. So the value produces is 312. Always we have to remember that the remainder part we have to produce. So this is always less than the value of the base. So always it is in the range. So the range of base 4 is 0 to 3. So we have to define that is the answer is correct in this form. This is the 312 is the answer. So this is the decimal to the any base. So it is at this time the base is 4. Now octal to binary. How we have to produce the value octal to binary? So first you have to convert the number in the binary in how many bits? Because the octal number is 8 and 2 to the 3 equals to 8. So we have to take the number representation in 3 bits in the case of the octal to binary, because we have to represent the number of this any decimal number into binary. In the case of the octal we have to take the 3-bit number. So if if the representation of 2 in the octal number representation form, so we will take basically the decimal number to the binary is 10, but in the octal representation we have taken the 3 bits. So it is basically 0 1 0. Same in the representation of this, if we have the number is 634, then we have to convert this particular octal number into binary. Each and every number we have to represent in the 3-bit form. So 634 it is basically 110, because the representation of 6 is corresponding to 8421. These are the weighted codes. This is basically 2QR0, 2QR1, 2QR2, 2QR3. So 2QR3 is 8, 4, 2, 1. Same procedure we have to follow for the next position value. There are 2QR4, that is 16. So when we have to calculate the binary value from the decimal number, so this is the direct method. This is the weighted code methods 8421. So when the value is 634, so the representation is basically 110, because 4 plus 2 is 6 and this is the 0, so it is 110. Now the representation of binary number from the decimal of 3, so it is basically 0 1 1, because we have to represent the number into 3 bits in the octal form, and the binary value of the 4 is 1 0 0. So basically the number representation is 110 0 1 1 1 0 0 with the base 2. So this is the representation of octal to binary. Now take the another example, that is 546 base 8 converted to base 2. Then how we have to represent this number? So basically the representation of 5 in 3 bits, that is 101. Directly you have directly converted the number by using the weighted codes. So this is 4 plus 1 5, so this is 101. Now the 4 is 100 and the 6 is 110, that I already take in the previous example. So this is the resultant, that is 101, 100 and 110. So this is the basic conversion from the octal to binary. Now the next example is hexadecimal to binary. So you know that hexadecimal numbers are represented to 0 to 9 in the same as a decimal number. After that 9 number we have to represent 10 as A, corresponding 11 as B, 12 as C. So this is basically 3FD. When we have to represent the hexadecimal number into binary form, then hexadecimal number means base 16, and when the number representation in the 2 to the power how much we have to use the number value for representation of 16. So it is basically 2 to the 4 equals to 16. So how many bits we have to use to represent the number of the decimal number of the hexadecimal number in the binary form? So it is basically in the 4 bits. We have to use the 4 bits in the hexadecimal number system and the 3 bits in the octal, because the base value of the octal is 8 and the base value of the hexadecimal is 16. So in this case, we have to represent each and every number of the hexadecimal number in the binary form in the 4 bits. So 3 is converted as 0, 0, 1, 1. F, that is means 14 or 15. That is 15 basically, because 14 represented as E, that I already explained in the previous slides. Just a minute. This is the number value representation. So this is 15 is as F. Okay. So this is the number conversions. Now the value of okay. So this is F. F is represented 15. So it is basically 1, 1, 1, 1. So it is 15 because 8, 4, 2, 1, calculated 8, 4, 2, 1, it is 8 plus 4, 12 plus 2, this is 14 and 1, 15. So it is 1, 1, 1, 1 and D representation is I think 13, okay, 12 is C, so 13 is D, so it is 1, 1, 0, 1. So this is the answer of base 16 to base 2. Now the second example is 28F. 28F, so each number we have to represent to 4-bit form. So it is basically 0, 0, 1, 0, 1, 0, 0, 0 and it is F value is 1, 1, 1, 1. So this is the number representation of base 16 to base 2. Now the next conversion is binary to octal. So binary to octal means base 2 converted to base 8. So when we have to convert it from base 2 to base 8, then again we take the 3 digits as a used for the conversion from the binary to decimal. So we group the 3 digits as a combination for corresponding to defining the number from binary to octal. So when the number is 1 triple 0, 1 0 0 1 1 0 1 1, then we have to grouping from starting from LSB to MSB with the 3 bits. So this is 3 bits. This is the grouping of 3 bits, this is the grouping of 3 bits, this is the grouping of 3 bits. So the number is 0, 0, 0, 1, 1 is basically 3, 0, 1, 1 this is basically 3, this is the 0, 1, 0 that is 2 and 1, 0, 0 that is 4. So converted number is 4, 2, 3, 3 base 8. In this particular example, we take the grouping of 3. How we take the grouping of 3 in this binary to octal, because the base is 8 and in the 2 to the power position form, so it is basically the conversion of 2 to the 3. So we take the 3 bits as a grouping in the binary number conversion from binary to octal. So this is the basic conversion rule. Okay, one thing that you have to always keep in mind, that if in the MSB part we have to left only the 1 digit, then we take the 0 0 in this form for completing the grouping number, that is 3. Suppose let's take another example. Suppose this is a number and we have to convert this binary number to the octal. Then how we have to convert that? Then we take the grouping 3 in this form like this, and this is the single number we have to left. So we take the 0 0 as the MSB part, because this is no means. So it is basically 1. So it is 1. It is 1. The answer is 1 1. It is in binary. Oh, sorry. This is in octal. So this is the number representation from the binary to octal. And now this is also the binary to octal. So it is what? It is basically, this is 3, 3, 3 and this is 3. This is take the 0 0 for completing the grouping number from the 3-bit number digits grouping. So it is basically, it is 4, it is 7, it is 3 and it is 0. So answer is 0374 from binary to octal. So this is the conversion. Now the next is binary to hexadecimal. How we have to convert the hexadecimal form? When any number we have to give it in the binary form and we want to convert from the binary to hexadecimal, then we have to group by the 4 from starting from the LSB to the MSB. Then take the grouping with 4. This 4, this 4. So it is basically what? 1011. 1011 is B, 1001 is 9, and 1000 is 8. So the answer is 8, 9B in this form when the binary to the hexadecimal. Now this is the next example. So how we have to calculate? We grouped from the LSB to the MSB. So this is one group, this is one group, and this is the grouping of 3. But we have to use the 4-bit grouping. So we take the MSB value, that is 0 in this form. And the answer representation is, this is basically 12. So 12 is represented as C. This is 15, that is F. This is 0100, that is the 4. So 4CF base 2, this is the resultant value. Now the next conversion is octal to hexadecimal. When we have to convert any number from octal to hexadecimal, then first we have to convert the number from octal to binary, then binary to hexadecimal. So the example is 615. So first we have to convert the number into the binary form, then the hexadecimal form. So 615, first you have to represent the number in the binary form. So you use the 3 bits for each number, because you have to convert the number into the octal form, sorry, octal to binary form. So the number of 6 representation of in binary is 100, because you use the 3 bits in this for the grouping. 1 is 001 and 5 is 101. When we have to convert the number from octal to binary, then again we have to convert the number from binary to hexadecimal, then take the 4-bit grouping because of the base 16. So obviously we take the 4 bits as a group in the hexadecimal form, or converting the number from binary to hexadecimal form. So it is basically the grouping of this, this and this. So it is 18D. So this is the conversion of octal to hexadecimal. Let's take the second example, that is 567 base 8 converted to base 16. So first you have to convert this number into the binary form with the grouping of the 3 bits. So it is basically 101, it is 110, it is 111. This is the conversion of octal to binary. Now when you have to convert the number from binary to hexadecimal, then use the 4-bit grouping. So it is basically, it is 4, this is the single bit. So you have to put the 30 in the MSB. Then a number is 1. This is basically 8421. So this is basically 7. This is basically 7. So number conversion is like that. This is 177 is the answer. Now the last is the hexadecimal to octal. So same procedure we have to use from hexadecimal to octal. First you have to convert the number from hexadecimal to binary, then binary to octal. So this is the same procedure. Let's take an example, 567B. Base 16 converted to base 8. So first you have to convert this number in the binary form, but in the grouping of 4, because you have to convert the number from hexadecimal, and hexadecimal means we have to take the grouping of 4. So this is basically 0101, this is 0110, this is 0111, this is the B, this is the 11 representation. So it is basically 1011. Now this is the number representation of hexadecimal to binary. Then again, when we have to convert this number into the octal form, then take the grouping of 3. So it is the grouping of 3. This is the grouping of 3. So it is basically 3, 7, 1. Now it is 3. It is 5. This is 0. So 053173 base 8. This is the answer, and always we have to check the answer that the range of each value that produce as an answer, if the base is 8, then the range, each value in the range, that is 0 to 7. So this is the correct value of the answer, or check the answer. And these are the examples for you guys. You have to just convert the numbers, and if you have any problem, then you have to clear with my examples that I already explained in the slides. So thank you so much for this particular lecture.